Hello, in this video we are going to start discussing alkenes in preparation for learning about elimination reactions. So if you have the third edition of the Klein textbook, the elimination reactions are kind of scattered throughout the 7th chapter. However, if you have the second edition of the Klein textbook, the elimination information is in chapter 8. So that can be a little confusing. So if you have any questions about which chapters you should be reading or looking at, just let me know, and I can kind of help you figure it out. So again, chapter 8 for the second edition is elimination reactions. And then chapter 7 in the third edition has both substitution and elimination reactions mixed together. Okay, now before we can talk about elimination reactions, we have to talk about alkenes. So we're going to learn how to name alkenes. So this will be somewhat similar to how we've named other molecules. We're going to identify the longest carbon chain that contains the alkene, so the double bond. And then we're going to number the chain so that the double bond is always at the lowest position. So this is kind of treated like any other functional group. Then we're going to identify substituents. And then we'll arrange the substituents alphabetically in the name. And then we're going to use cis, trans, or EZ to identify stereochemistry. And that specifically will be around the double bond. And then we just change our suffix to -ene. So remember, with alkanes, we used ANE at the end. But with alkenes, we use ENE. So in general, the way this will go is we'll start with any stereochemistry in parentheses, and then we'll list our substituents in alphabetical order. And then we're going to list the numbers or the specific carbons that the double bonds are located at. I don't know quite how to say that right? I'm tongue-tied. It's getting towards the end of the quarter. And then we'll name the parent chain. So we'll just list, for instance, hex or hept or oct, depending on how long the carbon chain is that contains the double bond. And then at the very end, we're going to write -ene to indicate that we do have a double bond. Now, sometimes chemists will put the number in front of ENE, so sometimes it will look like the following. Oops, actually, forget that dash there. Parent dash number dash -ene. So sometimes they tuck the numbers in right before the ENE, which is a little strange to me, but just so you're aware, there are two different ways to name alkenes. All right, so let's go over some examples. So let's start with something that's fairly simple. Okay, so how would we name this molecule? So let's first identify how many total carbons we have. So it looks like we have 1, 2, 3, 4, 5. And let's number them so that the double bond has the lowest number possible. So I'm going to number starting from the left. 1, 2, 3, 4, 5. and the double bond starts at carbon 2. Now, if we had numbered the opposite way, from right to left, you can see that the double bond would start at carbon 3, and that's higher than 2, so that is the incorrect way to number that chain. Okay, so we can already start by writing pent for 5, and then ENE to indicate that we have a double bond. And then I'm going to put a 2 in front to indicate that the double bond is at position 2, or it starts at position 2. And then it doesn't look like we have any substituents, so we just have to figure out if this is cis or trans. Now you could try to assign E or Z to this as well, that works too. But since we do have hydrogens bonded, and those are the same type of group, we can just use cis or trans. All right, so is this a cis molecule or a trans molecule? So the hydrogens are opposite each other. Additionally, the carbon groups are opposite each other on the double bond, so that should be trans. So this is trans 2-pentene. Or remember, you can also write this as trans, pent 2-ene. So sometimes they put the number right before the ENE. All right, let's try another one, and I'll make this one a little more challenging. Okay. All right, so if you want to pause the video and try this one on your own first, you can. And then when you unpause, we'll go over it together. Okay, so let's count out the total number of carbons in our longest chain. So I'm seeing 1, 2, 3, 4, 5, 6, 7 in the longest chain. And let's see, how do we want to number this? So we want to give the double bond the lowest number possible. So I think we have to go left to right. Okay, yeah, if I had gone the other way, that would have been at position 4, whereas with the blue numbering from left to right, that's at position 3. So yes, we do want to go left to right for this one. Okay, so we can already start by writing heptene, because hept stands for 7. And we already can see that the double bond is at position 3, so we'll just add a 3 dash in front of heptene. And then it looks like we have a few substituents. So we have 3 methyl groups, and they're located at position 2 and position 5. So we're going to write 2, 5, so 2, 5, 5, dash trimethyl dash 3 heptene. Okay, and then the last thing we have to do is figure out if this is a cis or trans double bond. So are the carbon groups on the same side of the double bond or opposite sides of the double bond? Opposite. So this would be trans 2,5,5 trimethyl 3-heptene. And again, remember, we could have also tucked those, or that double bond number right in front of ENE. Okay, let's try one more molecule, and I'll make this one challenging as well. Okay, so now we have a ring. So see if you can name this one on your own first, and then we'll go over it together. All right, so remember when we were naming alkanes, the ring system was automatically the parent chain, unless, of course, you have a ridiculously long straight chain coming off of it. So we're going to number the ring so that the double bond starts at the lowest number possible. Now, additionally, we have some substituents. So we also want the substituents to have the lowest numbers possible. So for instance, I would start up here, 1, 2, 3, 4, 5, 6. Now, we wouldn't want to start, let's say, at the other side of the double bond, because that will give that methyl group at the top a position of 2, but we can see from the blue numbering scheme that we could give that methyl group a value of 1. So that's the better numbering scheme. So in this case, we kind of had to think about the double bond and the substituents at the same time and make sure that everyone gets the lowest numbers possible. All right, so this tells us that we have cyclohexene, and for ring systems, we typically do put the number for the double bond right in front of ENE. It's just a little bit easier for ring systems. And then we have a few substituents here. We have a methyl group at position 1 and 2 methyl groups at position 4. So we would list out 1, 4, 4, trimethyl cyclohexene. And then for ring systems, we actually don't use cis or trans. So if you were struggling a little bit with how to assign that, don't worry. Let's add a little note. We don't need cis-trans for rings. At least for rings that are less than 8 carbons. So once you get up to cyclooctane, for instance, or octene, I guess, then things get a little tricky, but when you have a ring system, the positions of your substituents are already kind of decided for you. So you don't have to indicate whether they're cis or trans. All right, and then let's just review EZ nomenclature a little bit. It's been a while since we've gone over E and Z. So let's say that we have the following molecule. All right, so remember, if you have 4 different groups bonded to your double bond, then you can't really use cis or trans because it's hard to figure out, what takes priority and, what are we looking at to decide whether things are on the same side or the opposite side. So instead, we use the E or Z designation. All right, so remember when you're assigning E or Z, you assign the first and second priority groups or second priority substituents coming off of each carbon in the double bond. And then if the highest priorities are on the same side, that is Z. And if they're on the opposite sides, that's E. So you might also be wondering, wait, how do we decide what has higher priority again? So it is going to be based off of atomic mass. So whatever has higher mass will have higher priority. All right, so that being said, let's name the molecule up above. So let's find the longest chain that the double bond is a part of. So that might be a little tricky. So let's start up here. 1, 2, 3, 4, and then let's go to the left. 5, 6. Okay, that's 6 carbons, but it looks like there's more carbons going off to the right. Okay, so let's do 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's 8. But what if we start down below? So what if we start 1, 2, 3? Oh, but the double bond, if we kept going, wouldn't be a part of the longest chain, so that doesn't count. So I think the red numbering scheme is probably the best one here. That gives us the longest chain, and the double bond is in that chain. So that's important too. All right, so I'll just rewrite that numbering scheme. Hopefully I don't erase too much of this molecule. There we go. Let me just kind of fix these bonds here and we'll rewrite that numbering scheme. All right, so 1, 2, 3, 4, 5, 6, 7, 8. And we also gave the double bond the lowest number possible. If we had started from the right and gone to the left and up, the double bond would have had a much higher location number. Okay, so it looks like we can start by naming this octene, and the double bond is at position 3. Okay. So now let's figure out what our substituents are. So it looks like we have a fluorine substituent and an isopropyl substituent. So we have isopropyl and fluorine. And we want to alphabetize these substituents. So what comes first? Does F come first? Oops, I zoomed in. Or does I come first? F comes first. All right, so we would name that as 3-fluoro because it's at position 3. Dash, and then isopropyl is at position 4. Oops, I might not have enough room, so I'll rewrite the end of the molecule here. All right, so far we have 3-fluoro, 4-isopropyl, 3-octene. And now we have to designate whether this is E or Z. Okay. So let's prioritize the groups on each of the carbons in the double bonds. So let's start with the carbon at the top of the double bond. at position 3. So that is bonded to an ethyl group to the left and then a fluorine to the right. So it's bonded to a carbon and fluorine. So in a competition between carbon and fluorine, which one is heavier? Fluorine. So fluorine has a higher atomic mass, so that will have priority 1, and then the carbon in the ethyl group has priority 2. Okay, so now down below, let's look at carbon 4. Let's figure out which group has first priority. So initially, we're comparing 2 carbons on the left and the right. And let's see what those carbons are bonded to. So I'm actually going to highlight the carbon to the left in orange. And so we're going to compare the orange carbon, and then let's compare that to green. So the orange carbon and the green carbon. What are they bonded to? So the orange carbon is bonded to 2 other carbons, and then there's also a hydrogen in there that we just didn't show. So that's carbon, carbon, hydrogen. And then the green carbon is bonded to another carbon, carbon 6. And then there's also 2 hydrogens that we didn't show. All right, so which one wins, the orange carbon or the green carbon? The orange carbon, so that would be priority 1. Green carbon would be priority 2. All right, so looking at our priorities, let's compare the 2 highest priorities, fluorine and isopropyl. So are those opposite each other, or are they on the same side? They're opposite each other. And we said that if they're opposite, we give that an E designation. So we're going to write E in parentheses, -3 fluoro, -4, isopropyl, -3, octene. Whew, okay. So hopefully that was a good refresher of how to use E and Z and when to use E and Z. So let's do one more practice problem, and this is going to be a challenge problem. So in this one, there are going to be multiple double bonds in the chain. Oops, I zoomed in again. Okay, so this is our molecule. And if there are multiple alkenes, you can use a prefix in front of ENE to indicate that you have multiple alkenes. And you also have to show the number for each different alkene. So for instance, if you have 2 alkenes, you would call that a diene at the very end. If you have 3, that would be triene. And if you have 4 alkenes in the chain, that would be tetraene. And I actually do recommend putting the numbers in front of the, let's say, diene or triene or tetraene. That'll be a little bit easier to write out. Okay, so if you want to try this on your own first, you can pause the video. If not, we can keep going. So I'll just pause for a second to let people figure it out if they want to. All right, so let's try to find the longest chain that also includes all of the double bonds. So I think I'm going to start on the left because that will give the first double bond a position of 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, that should be our longest chain. So we can start by saying, okay, there are 3 double bonds, so that's a triene, and the double bonds are at positions 1, 4, and 6. And remember, we're always listing where the double bond starts. And then we can also add in front nana to indicate that we have 9 carbons in the longest chain. All right, so now let's list where all of our substituents are. So we've got a chlorine, a methyl, and another methyl. Okay, so what would come first alphabetically, chloro or methyl? Chloro, right? Because it starts with C. That comes before M. So let's see, we'll list 5, 6, 7. Oh, this is going to be complicated. I'm actually just going to rewrite the name because I might run out of room again. It's so tough to write these. Okay, so we have, let's actually start with the chlorine since they come first. 1,1-dichloro. And you do have to list each number twice, even if the chlorines are on the same carbon. It's a little redundant, but you do have to do that according to the rules. And then dash 5, 6, 7. Let's see. Trimethyl. And then nana dash 1, 4, 6 triene. Okay. So now we have to also indicate the stereochemistry at position 1. And then at position, actually at position 1, we don't have to indicate the stereochemistry because one of the carbons is bonded to 2 of the same group, a chlorine and a chlorine. So it would be impossible to figure out if that's E or Z because we can't prioritize either of those chlorines because they're the same. So we can actually ignore carbon 1 in that sense, but we do have to indicate stereochemistry at carbon 4 and 5. So we'll try to figure out the stereochemistry around that double bond. And then also at 6 and 7, so that double bond. What's the stereochemistry there? All right. So let's start with our double bonds between carbons 4 and 5. And it looks like there are 4 different groups bonded to that double bond. So we do have a hydrogen up above there at carbon 4. So let's prioritize those groups. So let's start with carbon 4 and prioritize the 2 groups bonded to carbon 4. So we have a carbon and a hydrogen. So which one would have higher priority? The carbon, right? So that would be priority 1, hydrogen's priority 2. And then looking at carbon 5, let's prioritize those groups. So we have a methyl group down below, and then carbon 6 off to the right. And we already know that on a methyl group carbon, that's just bonded to 3 hydrogens, right? Whereas carbon 6 is bonded to more carbons down the chain. So that would have higher priority. All right, so are the higher priority groups on the same side of the double bond, or are they on opposite sides? Opposite sides. So those would be, so let's see, that would be an E designation. So what we would write in parentheses at the front is 4E. So that tells us that the double bond at position 4, or the double bond that starts at position 4, has an E configuration. All right, and then let's go to carbons 6 and 7. So let's figure out the priorities there. And this one's actually a little bit easier because we do have 2 methyl groups, right? And those methyl groups are going to be opposite each other. And then looking at the other groups that are bonded, so if we look at carbon 5, for instance, and actually let me use a different color here. So we're looking at 6 and 7. 6 is bonded to a methyl group and then a carbon group off to the left. So the methyl group would have lower priority, right? Compared to carbon 5, which is bonded to more carbons. Oops. And let me actually erase that one there. These are getting confusing. And then at carbon 7 is bonded to a methyl group, and this carbon 8, which is bonded to more carbons down the line. So carbon 8 would have first priority because it's bonded to more carbons, but the methyl group on carbon 7 would have second priority. So on this one, we could say that this is trans because we do have 2 of the same groups. We have 2 methyl groups bonded to that double bond. However, we can also say that it's E. And that might be easier for what we're doing down below in our naming scheme. So we could call that 6E. And that's a little more consistent with how we're trying to name this molecule. Okay, so again, this is a challenge problem just to kind of get you thinking. So the name is super long for this one. We have 4E6E11 dichloro, 5,6,7 trimethyl, nano-1,4,6-triene. So some chemicals in chemistry are just insanely huge and have really crazy names, but at least we kind of saw how to name a molecule that has multiple double bonds. All right, so I do recommend going over the skill builder exercises in your textbook again. That helps a lot with practicing how to name these molecules. Additionally, this is going to be important going forward because elimination reactions do involve double bonds or alkenes. So we are going to keep talking about those in future lectures. So I will see you in the next video.